to give this additional lecture this afternoon at US time, which will be 10 o'clock in the evening for me, but still okay. So since I have more time, I just want, before going into partial exchangeability, I want to go just a second back to a thing I skipped yesterday. And yesterday I emphasized a lot the fact that there's this kind of general structure which appears in the posterior distributions. And this general structure, when you work with models given by transformed, completely random measures, and which appears somewhere hidden, somewhere always. Okay, in the normalized case, it's conditionally on a certain latent variable un, which we defined yesterday. In the neutral to the right process cases, you don't even need a latent structure, you get it immediately there. In other cases, and we will see also in the partial exchangeable case, you still get that type of structure, but there also the latent structure will be a little bit more complicated. So in a sense, let me tell you, the fact that you have to look for a structure like this, okay, so an updated CRM plus fixed points of discontinuity at the observations or at the latent variables with some random jumps. I mean, it's not a free lunch in the sense that you have the posterior of CRM-based model, and you know that that's the posterior, and then it's easy. No, the thing you know is that you have somewhere hidden that object, and you have to uncover it. Okay, and so it's not a free lunch to get there, but you know where you have to get. It's a bit like in mathematical analysis, when you kind of know what the limit should be, and then you play around sometimes even with the topology to get to that limit. Okay, and the topology in this case would be the latent structure you have to identify. You have to identify a suitable latent structure so to uncover this object. Okay, but so just to give another example of how that structure is always there, let me just discuss the Pitt-Magnol process very briefly, and then I start with the proper lecture of today. So you can actually, the Pitt-Magnol process, I mean, it's a special case of a Gibbs-type prior, but you can also recover it from normalized random measures with a little change of things. Okay, so if, for instance, here you have the construction, you can construct in several different ways, but that's an interesting one. You take a generalized gamma CRM, which we know it's now we kind of understood. We have to forget, as I said yesterday, about densities. We work with Levin densities. And so we have this generalized gamma CRM, which is characterized by the corresponding intensity measure, which is of this form. So you see you have the stable component here, that sigma here, which makes the heavy tailness of things. And then on top of that, since it's generalized gamma, you have also the gamma part here. Okay, so it's kind of mixing up a gamma random measure with a stable random measure. So you get both as limiting cases. Good. Then if you place a prior on the total mass base parameter of your completely random measure, and specifically this type of gamma prior, okay, then you get a mixture of generalized gamma completely random measures. So if you want, actually you could, as Ramses also pointed out yesterday, you could rephrase everything in terms of exchangeable random measures, so in terms of a more general framework. So in fact, what you would obtain by mixing a generalized completely random measure, what you obtain is an exchangeable random measure which doesn't have independent increments anymore, or is not properly a CRM, but conditionally on something, in this case on the hyperprior you put on theta is again a CRM. Okay, so that's essentially an exchangeable random measure. If you normalize that object, which I said is not a CRM anymore, then you obtain the Pitt-Magnol process. So in a very similar way, so I mean, a slight variation of the normalized generalized gamma process. Good, so in this case, I have then my Pitt-Magnol process. The posterior characterization you can give resorting to this underlying normalization construction is again in terms exactly the same way of the normalized random measure. So given your data, given a latent variable un, which in this case will have a certain form, which is this one, which is obviously different from the one you get in the generalized gamma case. Okay, but conditionally on un and on xn, you get again this nice structure. Okay, this nice structure, which in this case will have underlying an updated CRM, which is a generalized gamma one. You will have again gamma jumps, and obviously the jumps and the completely random measure are independent. Okay, so you get essentially the same posterior structure you have for the normalized random measures. also for the Pitt-Manure process, which is the most notable case of Gibbs-type priors. Good, but we all know, obviously, that for the Pitt-Manure process, probably most of you know, there's a simpler, if you want, a simpler posterior characterization, which is the one I have in this slide, in the following slide, and you actually obtain it immediately from the one I showed you now. Okay, so that's probably the posterior characterization, you know, okay, that's the one which goes back to the paper by Pittman in '96, where it tells you that that's now not with respect to a latent variable, but directly with respect to xn, okay? So you have that the posterior of the Pitt-Manure process given xn is a mixture between this process, this random probability measure here, which depends on kn, which is again a Pitt-Manure process with updated parameters, plus some point masses at the observations, at the distinct observations. And jointly, the masses attached to the observations and to this updated Pitt-Manure process, they have a Dirichlet distribution like this. Okay, that's the most popular posterior representation of the Pitt-Manure process, which is given by Pittman in '96. Okay, the point is, which I want to make here, that this representation, you immediately obtain it by marginalizing out, and in the Pitt-Manure process, you're able to do that, but marginalizing out this posterior representation. Okay, so the crucial thing I want to say here is that underlying even simpler posterior representation, there's always this structure in terms of a completely random measure plus fixed points of discontinuities with random jumps, which is not apparent if you look at this one, okay? But the deep posterior structure is the one I showed in the slide before, okay? It might be a little bit more involved since it's also conditionally on a latent random variable, but there is where you see really what's going on behind, okay? Then you obviously, from a concrete and from an implementation point of view, you try to obtain the expression which is as simple as possible, right? But the deep structure is the one I showed you before. So again, also in the Pitt-Manure process, you obtain this nice structure with updated CRM plus fixed locations with random jumps. Okay, and then from this one, it's straightforward to obtain the predictive distributions, which then degenerate to the Dirichlet case if you take sigma equal to 0. Just another little thing I want to mention, you cannot really hope to get such a simple representation in many other cases, because that's kind of a side thing I want to say. The fact here that you hear, that's actually the process generating now new values, okay? And that's a characteristic, again, of the Dirichlet, obviously, because it's conjugate, and of the Pitt-Manure process. So the Pitt-Manure process is the only process for which here you have the process generating new observations is again of the same type. So in this case, it's a Pitt-Manure process with updated parameters. Okay, but the point I wanted to make is that again, you have this nice posterior structure. Good, so given this, as I said yesterday, now we move on to, partial exchangeability, okay, which is kind of the obvious generalization of exchangeability. And so we go through quite a long list of things, and so thankfully I have 2 hours, so I'm able to go through hopefully all of it, if not all, then most at least. And we start from partial exchangeability, and then first thing, which I think is important, which hasn't been done much and hasn't been done even in the probabilistic literature, trying to understand the dependent structure implied by partial exchangeability. Okay, so first thing, if you want to understand a dependent structure, is obviously to go and look at extreme cases. And second thing, once you understood well the extreme cases, you want a measure of dependence. Okay, and that's most of the literature focus for now on correlation, which I'm not too happy about. And so we actually propose a different approach, which is a principled approach, distance-based approach to measuring dependence. And we spent some time on this one, which is, I think, a nice chapter. Once we, understood is a big word, but once we are a bit more into what kind of dependent structure we can achieve, then we go and look at several classes of based on parametric models. And in particular, we go through 3 natural constructions for dependent non-parametric priors, which are additive structures, hierarchical structure, and then tomorrow we will see also nested structure, which are 3 kind of natural and popular ways of constructing them. Okay, so we go through them for one by one, and then tomorrow actually we try to put them everything under just one hat, which is that of compositions of random measures. Okay, and, putting that under the framework of compositions of random measures, you get them all as special cases. But for now, we go one by one because we need to understand. Okay, first you need to understand what's going on, and then you can try to unify things. So good. Then, as this slide I actually showed you already yesterday, that even Definetti himself saw exchangeability just as a limiting case. Okay, but it's still the limiting symmetry, which is your possibility, and we still have analogy. So we always look for kind of symmetries because that's what allows us to make inference. Okay, and in particular, partial exchangeability will be the kind of symmetry where you have different experimental conditions. So you have a homogeneity within each of them, and homogeneity means then to have exchangeability within each experimental condition. So think, for instance, about meta-analysis situations where you have different hospitals in which patients are treated for the same disease. So within each hospital, you will have exchangeability, but you will have some heterogeneity across them. Okay, so you have these different experimental conditions, and that applies for a series of applications. Obviously, topic modeling is a very popular one, especially in machine learning. More classical in statistics, the two-sample problems, non-parametric regression, in particular covariate index data, time-dependent data, change point problem. I mean, partial exchangeability is really a nice and general framework to work with. Okay, and so let me introduce it formally now, what partial exchangeability is. Okay, so partial exchangeability, as I said, homogeneity within, heterogeneity across, but still dependence. Okay, so an array will be partial exchangeable, and always we will take infinite infinite arrays. So, okay, so even if you have a finite one, you can just think of it like it could be let's go to infinity. Okay, it doesn't need to be infinite, just in principle you should allow for that. And then you suppose that the distribution is invariant with respect to permutations within each of the two samples. Okay, here for simplicity and in the whole slides, I focus on the case of just two populations or two samples from two populations. And so you have exchangeability within each of them. So that's invariant, the distribution with respect to a permutation within each of the two samples. But you don't have exchangeability across. Okay, and here I have a very simple example. So the homogeneity within. So if I permute the first two values of the first sample, then the distribution won't change. But obviously, if I start permuting across, then I lose the homogeneity. Okay, so for instance, here, if I permute the second value of the first sample with the third value of the second sample, and so I do a permutation across the two samples, then I obviously lose the equality in distribution because exchangeability doesn't hold across. So you have heterogeneity across the two populations or the two samples. Okay, so far so good. Thankfully, and it's not a kind of a big generalization, given the whole context, we have also a representation theorem in this case. Okay, so we have a representation theorem which tells me that if I have the two samples, then I can always represent that in integral form with respect to a Definetti measure Q, which now lives on a two-dimensional space, the two-dimensional space of the probability measures. Okay, and so conditionally on Q, within each sample, they will be IID. Okay, so if you want to write it in hierarchical form, that's the way to see it, that they are IID given a realization of your Q, which is now a product measure. But the point is that those, the P tilde 1 and P tilde 2 now are dependent, so I need to work out a vector of dependent random probability measures, which is not easy. In a certain sense, what we are back to square one. Okay, so as I mentioned in the first lectures, kind of the theoretical framework of Definetti was laid out between the 20s and the 30s, and then it took up to 1973 to get a breakthrough in the sense of having a concrete non-parametric prior to work with, and was the Dirichlet process by Ferguson. The same here. Okay, we are back to square one in the sense that now we know how to construct a single random probability measure, but we really don't know how to construct a vector of dependent random probability measures. Okay, so once we tackle partial exchangeability in a certain sense, we're back to square one. Again, we are missing, as if I use now Lindley's words, we are missing the technical tool for doing inference. Okay, in principle, we know what we need. Okay, we need a vector of random probability measures which are dependent, but the point is I need something tractable. And for me, tractable in a Bayesian context means I have to be able to work out somehow the conditional distributions, the partition distribution, the predictive distributions. Okay, and so that's what the first goal. Okay, and the first kind of really the pioneers in this context, so the analogs of Ferguson for the exchangeable case have been Cifarelli and Regazzini, my both master's and PhD supervisor, and Steve McKeegan, okay, which in his papers in 1999 and 2000, they were the first actually to pose the problem in a sensible way and to try to tackle it, okay, to develop a dependent non-parametric. And just kind of as a side comment, it's not a coincidence to me, the fact that if you look, this one is a technical report. And even, I mean, the papers of Steve McKeegan, one is a technical report and the other one is just published in the proceeding of ASA, of the JSM, okay? And it happens actually quite often. I think, for instance, even out the paper of Baron about frequencies consistency, okay, that's also a technical report, that when you really do something new, you have problems to publish it, okay? And so it's not a coincidence that really breakthroughs often end up being technical reports because they get rejected from journals, okay? So that's pretty interesting, I think, observations. And even in my own experience, I mean, I haven't done breakthroughs as Stephen or Eugenio or Baron, but still I kind of realized in my experience that when you do really something which is different from things which were done before, you have much more troubles in getting them published. When you do epsilon variations, it's typically a little bit easier. So the take-home message here, I think, is also for students: if you keep getting rejected a paper, either it's great or it's really crap. So there are no things in between, okay? Or probably it could be a breakthrough, it could be something which is really bad. Good, but then, so that's the first thing we need to do. Our goal is to introduce classes of dependent non-parametric priors, and so that's one with the pioneering, relying kind of on the shoulders of Cifarelli, Regazzini, and Steve McKeegan. And the other thing we need to do, and that, as I said, there's little even in the probabilistic literature to understand the dependent structures induced by this Q now, which is the law of a vector of dependent random probability measures. And once I understood it, also to develop some kind of measure of dependence, okay, which will be something not too easy, right? Because we are working on infinite dimensional spaces. Good, then let me just mention before proceeding, since we always have this focus on prediction, a very simple fact, which is almost trivial to prove, but it's, I mean, the first time I thought about it, it's not kind of so obvious. But so let me mention it also because it connects with things we mentioned in the previous lectures. So again, suppose I have a Q, and now I don't use any specific Q, okay? That's really a structural property, obvious, okay, but I think still interesting. Property of partial exchangeability. So I have a Q, and I have my vector of discrete random probability measures. Okay, as usual, I'm working with discrete stuff, so that's also the title of the lecture, so I'm working in the discrete case. So I will have ties within each sample and possible also across, possibly, okay? That's not necessarily, but possibly, and typically the cases which are of interest are those where you have ties across the two. Good, then let me take my two samples, okay? And the two samples will feature an overall number K of distinct species. Okay, and good, then I can have now of the induced partition, I can have two possible parametrizations. And according to the type of model I'm using, one or the other is more convenient. It's a little bit like with the species, no? That you had the frequencies or the frequencies of frequencies. So either I was looking at the frequency of each specific species, or otherwise I was looking at the number of species with a certain frequency. Here it's different, but still, no? Two equivalent parametrizations, and according to the problem you're dealing with, one or the other is more convenient. So the first one is I just work with the vector of frequencies. Okay, so I have k overall distinct species in the two samples, so values, whatever. Okay, and so Nij is then the elements in the ith sample, which is equal to the jth distinct value. And obviously, if you have this type of parameterization, you can have also zeros, right? For instance, if n11 and n is positive and n21 is 0, it means that this value is only present in the first sample and not in the second. So for a sample which is present, or for a value which is present in both samples, what you have is actually that both the same elements, the same coordinate of your vector has to be positive for the first and for the second vector. Okay, so if it's positive for both, it means that that's a shared value. Okay, so that's one parameterization. The other one is more explicit if you want, and more or less convenient according to the situation. There you really distinguish the k distinct values among, say, you say that you have k0 values which are shared between the two samples, k1 which are specific to the first, and k2 which are specific to the second. Okay, and so you have the shared distinct values which will have the corresponding vector of frequencies for the first sample and the corresponding vector of frequencies for the second sample. Good, then you have the k1 distinct, the k1 distinct value specific to the first sample with frequency r. Okay, and obviously the corresponding frequencies in terms of the first parameterization would be 0 for the other sample and for the second sample. Okay, so that's one parameterization. And then you can write down, and that's the goal of everything, especially we want to do clustering, you can write down formally what you need to compute. What you need to compute is the so-called partial exchangeable partition probability function. Okay, and that's a generalization of the PPF in the exchangeable case. So that's the function which characterizes the random partition induced by your model. Okay, and actually it's in the probabilistic literature, it's full of papers dealing with exchangeable partition probability functions in the exchangeable case, but there's almost nothing for the partial exchangeable case. Why is that? Because we as Bayesians, we get, even in the exchangeable case, we get to the exchangeable partition probability function by essentially marginalizing out the values of my sample, and then I have immediately my exchangeable partition probability function. In the partial exchangeable case, we do the same. Okay, so we have our two samples or J samples, and we marginalize out the values, and so we get to the notion of partial exchangeable partition probability function. If you just work directly with the partition, it's not obvious how to relate partitions, right? So it's much more natural for us to end up working with partial exchangeable partition probability functions. And so also from a probabilistic point of view, these are kind of completely new things to work with, okay? And I think they are also of interest independently of the Bayesian framework. But the nice thing is that we get to those in a natural way, okay? Because we work with the distributions of two samples generated from discrete, from a vector of discrete random probability measures, and so we have this partial exchangeable partition probability function. And so what we need to compute at the end of the day, here it's just written down formally because I haven't specified the random probability measures yet. So according to the first parameterization, remember the one in terms of the vector of size k, where you can have also zeros, you have to work out this integral here, the expected value of this integral. In the second parameterization, we will split them up according to the one specific to the first, the one specific to the second, and the one specific to the third. You essentially work it out in this way. Okay, so that's for the moment just formally, but it sets our goal. Okay, we want to compute those things. Once we have those things, then the partial exchangeable partition probability function, we can also compute the prediction rules and so on, and our key basic building blocks for every type of marginal algorithms. Okay, and so we want to work out at the end of the day those kind of objects once I made a specific choice for my Q here. Okay, for now it's still an open problem. How do we define a Q whose realizations is a vector of dependent probability measures? Good, but still before entering any type of model, Okay, let me just, as anticipated before, a structural property which is kind of straightforward but still interesting. Okay, so suppose I have my sample. We look at prediction over an additional sample. As I mentioned at the beginning, I really like that because you see the influence of the model. So I have my sample and I want to make prediction over the additional sample of size m, and I take the additional sample of size m over the first one. Okay. Well, you could do the symmetrically over the second one, but for now, look at the first. And suppose I'm interested in the probability of sampling values, say, which are already observed in X2, but not yet observed in X1. So I'm considering a model which shares the atom between the two, okay? So which has a positive probability of ties across the two random probability measures. So I want the probability of sampling values in X2, not yet in X1. So formally, I define this as the set A new old. So new with respect to the first sample, old with respect to the second sample. And with this one, then that's nothing else than the number of observations or values in the additional sample which belong to this set. So how many values which I already have observed in X2, but not yet in X1, will I observe if I take m additional values in the first sample, okay? And it turns out it's a little bit like for binomial distributions in the IID case, that it's m times the success probability. So it's the expected number of values or the additional sample of size m, which coincide with values in X2, which were not yet present in X1, is m times the probability of sampling at step n plus 1, n1 plus 1, here I forgot it should be a capital M, which belong to that set. So it's m times that, so it's linear in m, okay? So it's like in the binomial case, the expected number of successes, obviously here it's not IID, okay? But it's partially exchangeable, so conditionally, on the observed samples, you actually have the identity distribution, and that's why you get a structure like this. So that's why I'm saying it's actually in principle trivial, but one might not think about this. Okay, so like in the binomial case, the expected number of successes is n times, so the number of trials times the success probability, and here it ends up a little bit in the same way because of that conditional identity distribution. Okay, and that obviously holds true also for the second sample, and it holds true also if I look at, the other different possible combinations. So, for instance, if I look at the observations which were in N1 but not in in X1 but not in X2, if I look at observations which were already in both samples, or if I look at completely new observations. So you see, it kind of makes the pair with the simple exchangeable case where I was looking at the probability of sampling something new. Okay, here it becomes a little bit more involved because it could be new with respect to both samples, it could be new just with respect to one of the two, or it could be something which I already have observed in both samples. Okay, and obviously the same structural property holds that expected number of values which will belong to any of those sets is m times the probability that the observation at step plus 1 with respect to the sample size belongs to that specific set. Okay, which is nice, and this now takes on a little bit the role of the probability of sampling something new we had in the exchangeable case. Okay, so that's a very simple property, but again, we need to try to understand what partial exchangeability means, and this is a tiny little block to understand what kind of is going on. Good, but then again, still very in general, I'm not yet to the point where I want to understand to construct models. I want to understand what my dependent structure is. Okay, the first thing which I want to do when I want to understand the dependent structure is the extreme cases. And the extreme cases for the partial exchangeable situation, well, the first one is to have maximal dependence. So maximal dependence, what does it mean? It means that my Q degenerates to full exchangeability. Okay, that I formally have my values, my samples separate, but actually could just put everything together and analyze it as if it was just a single sample. formally, what does it mean? It means that your Q degenerates on the diagonal, in the sense that you have full exchangeability, means that the two random probability measures, so your vector, the two coordinates, the two components of your vector, coincide almost surely. And if you want to see it graphically, it would mean that it degenerates, your Q degenerates on the diagonal. Then concretely, all the models we will deal with will be somewhere around here. Okay, the realizations of the Q will be here, I mean, around that diagonal. So that diagonal is kind of your, how do you say, your polar star. Okay, you know that's your reference point. That's the maximal dependence, the generation on exchangeability, when you can just put all the data in a single pot, and that's your reference. Okay, so that's the maximal dependence of full exchangeability. The other extreme case is independence, right? Where you essentially have maximal heterogeneity, because there the one sample doesn't influence at all the other. So you don't have any kind of born of information. You cannot leverage on the other sample to infer something. So it's full independence. Okay, in that case, you model the two random probability measures as unconditional independent, and then what you can do, you're back again in some sense to the exchangeable case, and you can analyze each of them separately. Okay, because there's no gain in terms of inference of putting them together. Okay, so that's the maximal heterogeneity. Good, so those are the two extreme cases, which are kind of I mean, make totally sense. Okay, that's what one would expect, but it's good to pin them down. Okay, and it's clear that a first requirement one would want on a model is that I have some parameters such that I can, that parameter, ideally I can learn about how far I am from each of the extreme cases. Okay, so my model will have to cover, a good model in this case is a model which covers the whole range between full exchangeability and independence, ideally regulated by a parameter which, according to where I set the parameters, I'm either, I can, in the limits, I degenerate either to full exchangeability or to independence. And ideally, then I want also to learn where I am. Good, but then the problem of, once we understand that those are the two extreme cases, the problem is actually how to measure it, concretely how to measure it. So if I have a vector of random probability measures which are dependent, okay, then how do I measure the dependence? Okay, I could still take, and that's the obvious thing to do, to take exchangeability as the reference point. So I want kind of a distance from exchangeability, which is not easy, but in a moment we'll try to propose a solution for that. So the most popular one, and again, it's I think the reason is mostly because of mathematical convenience. The most popular one is to use correlation. Okay, so you compute actually the correlation between the random probability measure, the first one and the second one, which are now dependent on the same set. And it turns out that that correlation typically, and tomorrow we make that clear where that typically comes from and why that happens. Okay, that I leave it for tomorrow. That's still kind of work in progress, but I will talk about it tomorrow. The correlation that typically doesn't depend on set A, and so it's taken as an overall measure of dependence. It has also clearly some good things. Okay, some good things in the sense that the extreme cases are covered well. Okay, that's the minimal requirement I would ask to a measure of dependence. So I have that it's not exactly that, but it's a good proxy. Okay, in the sense that if I have perfect linearity, which means correlation 1, is actually implied by our extreme case of maximal dependence. So when p tilde 1 is equal to p tilde 2 almost surely, then I have perfect linearity and correlation equal to 1, which is good. On the other hand, if they are independent, okay, that implies some correlation. So it's kind of a good proxy. Okay, so on top of that, I said mathematical convenience. We haven't introduced them yet, but we will do soon. For instance, the thing that they give rise to very simple expressions. For instance, for the hierarchical Dirichlet process, the correlation between the two random probability measures of the two populations turn out to have this simple expression. Then I will discuss what these parameters are, but just to show you that you get very simple objects, okay? So that's also the reason of the popularity. I still don't have, how to say, I still don't think that's a good measure of dependence of the random probability measures, because random probability measures and linearity are something which actually don't match well together. Rather, and that's a thing we tried to do recently, I'll discuss tomorrow, you should actually rather look then at the correlation between the observables, okay, and relate the correlation between the random probability measures to the correlation between observables, and then study the correlation of the observables, okay, because that to me makes much more sense than looking at the correlation of the random probability measures, okay. But back to that tomorrow. For the moment, take it as a good proxy of a measure of dependence, at least in the extreme cases. So non-parametric priors, so the first ones to introduce, I mean, were Steve McKeegan in his nice technical reports at the end of the last century, essentially, and the way he introduced them were in terms of stick breaking priors, okay? So in terms of stick breaking priors, you have two random probability measures defined in terms of stick breaking, and you make either the weights or the locations dependent, or actually, or otherwise both, okay? So the thing you have is that actually the big pro of this type of construction is that it's straightforward to implement, especially conditional algorithms like the slice sample of Stephen Walker or the retrospective sample of Omiros Papaspiliopoulos and Garrett Roberts. So they allow you to straightforward implementation from a computational point of view. The cons is a little bit like I mentioned at the beginning, that stick breaking priors outside the Dirichlet a bit manual process, and you immediately end outside by making them dependent, don't allow to use don't allow to derive analytic expression. That's at least a big con, but from a practical point of view, there's certainly a success story. Good, and so there are essentially two parties now out there, like Steven, Peter Müller, also David Tanson. They belong to the party of the stick breaking users. So it's a little bit like the Trump voters. And then there's another party which I belong to, and it's the one which use completely random measures. Okay, so we are the Biden voters. And so let me consider this situation. Okay, it's just a generalization of the situation I considered yesterday. It's the obvious one, okay? So we say our random probability measure is a transformation of a completely random measure. In this case, I have a vector, and so I will have to transform a vector of completely random measures, okay? Well, with a suitable transformation, which I don't set now for the moment. I just take it general, I keep it general. So it could be obviously normalization, is always candidate, exponentiation, kernel mixtures, and whatever you want. Okay, but so before entering that type of approach, and I said I'm of the Biden party, so I go with completely random measures. I'm not going to break sticks. Before entering particular transformations and working out the related quantities, I want to introduce here a thing which I'm very happy about, that we managed to do this. And actually, I announced this that we wanted to do this when I gave the keynote lecture at the Bayes non-parametric meeting in Raleigh 5 years ago. So it took us 5 years to do this, and I was actually thankful. We have to be grateful to Marta Catalano, who's our PhD student, Antonio and I, because to crack this problem wasn't easy, okay? And without her help, it would have been really impossible to do it. And so what we tried to do, and I remember also during the talk in Raleigh, we kind of discussed that with David. So to make a principled approach to understand and quantify dependent structure in general and not more the specific framework, okay? And we kind of agreed, yeah, the Wasserstein would be a way to go, but I mean, just saying use the Wasserstein is not enough, okay? And so we need to do a little bit more. So the steps, I mean, along these years we understood we need to do is, so first of all, take the exchangeability, that was obvious, okay, as the reference point. So I measured the dependence as a distance, or in terms of closeness to exchangeability. Then another key step, which mimics a little bit what we did for deriving the posterior. As I said, you derive the posterior of the completely random measure, not of the transformed one. Then you can transform back. So suitably recast the problem in terms of the underlying random measures rather than of the transformed one. That has the advantage of yielding then a generic one, which is not dependent on the transformation you do of the underlying random measure. So you work with a vector of dependent completely random measure. So it's generic, it's not model specific. It doesn't depend on the transform you do. And then you define a certain distance, which is based on the Wasserstein metric, which is ideally suited for working with discrete structure, okay? Because they are not dominated things, and so the Wasserstein is actually the natural go-to distance you have to use. And I have to give credit to Long here, who was the first actually to use the Wasserstein distance in a Bayesian non-parametric framework, and it was really a nice breakthrough he achieved with his first paper in 2013. And then yesterday we heard that he has done a lot of nice stuff in the meantime, but much credit to Long for doing that. And I remember when hearing his first talk, I really thought, well, that's the way to go in this context, okay? And so again, like a little bit yesterday, I also want to leave the floor a little bit for a change now to Marta Catalano, who will show you a little bit about this measure of dependence we have been able to introduce, and so you don't hear just me. So Marta, I'm happy to leave you the floor.
Okay, so as Igor mentioned, we want to find a measure of dependence for those vectors of random probability measures that are achieved as component-wise transformations of dependent completely random measures. So the idea is that we want to find a measure that does not depend on the particular choice of transformation T. And to do so, the idea is to recast the problem in terms of the dependent vector of random measures. And moreover, we also focus on the case where the two marginal distributions are equal or more surely, because this allows us to focus only on the dependent structures. So a first thing that one has to observe is that when the two random measures are completely dependent, so when they are equal almost surely, we retrieve the case of exchangeability. So we can actually look at exchangeability as supported on this diagonal line, just as the picture that Igor showed you before. Okay, very well. Then our idea is to measure the dependence in terms of how close we are to the diagonal, and we will do it through a suitable distance between the laws of vectors of completely random measures. We will focus on a broad class of vectors of random measures which have jointly independent increments. Okay, so these extend the completely random measure to a multidimensional context, and for this reason we decided to call them completely random vectors, CRVs. So these couple of remarks on these CRVs. So first of all, they can also be represented as almost sure discrete random measures. And moreover, their law is completely characterized by an underlying Poisson random measure, which describes the law of the jumps of the two random measures and the set of common atoms. So in practice, if one wants to assign a law to a CRV, it is sufficient to assign the mean measure of the underlying Poisson random measure. And this mean measure is usually called the Levy intensity of the CRV. So our goals for this talk will be to define a distance between CRVs, express it or find a tight bound in terms of the Levy intensities so that we can actually perform analytical computations of this distance, and use them to evaluate the dependence in notable models in the BMP literature which use completely random vectors. So let's go with the first goal. As Igor mentioned, we defined the distance through the Wasserstein distance in what I find a rather intuitive way. So first, we consider the Wasserstein distance between the one-dimensional evaluations of the CRV. And then we took the supremum over all possible Borel sets. So the Wasserstein distance was that we use here is between probabilities on R2. Okay, so we already heard the definition yesterday of Wasserstein distance, but for those of you who missed it, I will just recall that a coupling between two probabilities, P and Q, is a distribution on the joint space, which has P and Q as marginal distributions. And so the Wasserstein distance can be defined as the infimum over all possible couplings of P and Q of the expected value of the squared difference. Now, this infimum is usually a minimum over very mild conditions. And in particular, it also has a degenerate form of the type x phi of x, where phi is a suitable measurable function, which is usually called the optimal coupling. And so one can interpret the Wasserstein distance as an optimal transport problem, and it is, you can actually see it as the minimum cost of transporting a pile of sand from one place to the other. And so, as we said yesterday, the Wasserstein distance has a long history and has been defined and studied in many different fields. But in these latest years, it has gained a renewed interest, both in probability, statistics, and machine learning. So this has also, this is also due to the fact that we can now compute the Wasserstein distance in a fast way and also approximate it. But of course, in our setting, this doesn't have much importance because we said that we want to perform an analytical evaluation of the Wasserstein distance, possibly in terms of the hyperparameters of the BMP models. So we chose the Wasserstein distance instead because of the fact that it gives a lot of importance to the underlying geometry of the space. And this makes it ideal to compare distributions that have different support, which is indeed our case, right? Because we said that exchangeability degenerates on the diagonal. And I would just like to underline that this property isn't shared by many distances, such as Hellinger, total variation, and also Kullback-Leibler divergence. Okay, so Wasserstein distance is really suited for our problem, but especially in R2, it is very difficult to compute it. So this is due to two facts, essentially. First of all, the fact that it is true that the infimum here is actually a minimum, as I said in the previous slide, but it is in general very difficult to find the optimal coupling phi. Moreover, even if we do find the coupling, we still have to compute a difficult bivariate integral, which corresponds to this expected value in the definition. Nonetheless, we managed to find a general result, which consists in finding the optimal coupling for every possible dependent structure of CRVs. And this, of course, determines also an expression for the Wasserstein distance itself. Now, if you look at this expression, you see that it depends on the CDF of the sum of the CRVs evaluated on a Borel set A. Now, this formula is quite complicated, and in some easy dependent structures, we can actually manage to evaluate it analytically. And for example, we can manage to compute it under independence. But in general, this is too implicit. And in particular, it does not depend explicitly on the Levy measure. And so this prevents a concrete computation of this quantity. Okay, so this brings to our second goal, which was to express the distance or find a tight bound in terms of the Levy intensities in order to be able to perform computations, analytical computation, of course. So in what follows, I will focus on homogeneous Levy measures, though what I say can be extended to the non-homogeneous case as well. So homogeneous Levy measures have a jump component that can be separated from the atom component. Okay, so I will be focusing on the jumps and that are described by the measure rho. So now rho is a measure that is supported on the upper right quadrant. And a crucial observation is that in order to recover exchangeability, we have to consider measures rho, which are supported on the diagonal. Okay, so diagonal, so once again, exchangeability actually corresponds to the situation of a diagonal. Okay, also if you restrict to looking at the Levy measures. Then there are some general properties that characterize all measures rho. So in particular that they have to have finite mean and finite mass outside of the origin. Then they are allowed to have infinite mass in a neighborhood of the origin. Okay, and as Igor told us yesterday, in most cases in the BMP literature, we actually deal with these Levy measures, okay, with infinite mass in the origin. Nonetheless, let's consider the case where the measure rho is actually finite, so has finite mass R, let's say. Then the induced completely random vector has a compound Poisson distribution. So the underlying idea for our result has been the following, that by removing a neighborhood of the origin, we actually find a compound Poisson approximation for every CRV. Very well. And this was crucial in finding this result, which is one of the highlights of our work, because we managed to bound the Wasserstein distance between the CRVs in terms of the Wasserstein distance between the jump distributions of the compound Poisson approximation. And these jump distributions are expressed directly in terms of the Levy measures. So in this way, we actually managed to accomplish our second goal. And this leaves us with the third and last one, which is to evaluate this tight bound for notable models in the BMP literature. So I just wanted to dwell on the fact that evaluate the bound explicitly does not is not immediate from this expression in the theorem, right? Because we still have to evaluate the Wasserstein distance between bivariate distributions. And we said that in general, this is difficult because we don't have an explicit expression for the optimal coupling and because we have to compute bivariate intervals. So what we did in general terms is that we managed to find the expression of the optimal coupling for all possible Levy measures. But then we had to find explicit techniques to actually compute the intervals for every class of models that we focused on. So we managed to use our technique to understand the dependent structures in the following situations. So first of all, additive structures. And I guess you will hear more about them in a few slides with Igor. Then we managed to treat compound random measures and also Clayton-Levy copulas. So in the next slide, I will give an example with compound random measures. I just wanted to recap what is the take-home message of what I said so far. So our idea is that we can build an intuitive distance between the laws of completely random vectors through the Wasserstein distance. And this provides a tractable and principled measure of dependence for BMP models that are based on generic CRVs. Okay, so I'll just give you an example to try to give you the flavor of the kind of results that we achieved. So compound random measures were defined by Griffin and Lazen in an interesting paper on GRSSB in 2017. So the idea is that they build dependent random measures with a two-stage procedure. So first, they consider a common underlying CRM, and then they perturb it in two different ways, mu1 and mu2, in such a way that the perturbation mu1 and mu2 are actually IID from a joint bivariate distribution H. So this provides a very general way of building CRVs. And a specific example that was treated in their paper is actually the one where the common CRM is a beta CRM with concentration parameter phi. And the joint distribution of the jumps is actually a product distribution with gamma marginals of mean phi as well. Okay, so what the authors proved in their paper is that with this couple nu0 H, one actually achieves random measures that are marginally distributed as gamma random measures. And moreover, that the parameter phi does not have any role in the marginal distribution of the random measures and only accounts for their dependent structure. But now if you look at phi, you both have it in the Levy measure and in the distribution H. So it's quite involved to understand what kind of dependence is actually induced by phi. And our techniques allow to quantify it through the Wasserstein distance. And we actually found a bound that depends on A, which is the total mass of the base measure of the common CRM, and a function that only depends on phi, the dependence parameter. So here in the plot, you can see how our bound depends on phi, and in particularly, as phi increases, we see that the distance goes to 0, and thus we approach exchangeability. So one question that you maybe can ask is, okay, but you are actually providing an upper bound. How can we have evidence of the fact that it is tight? And I guess that this graph could give some empirical evidence of this fact. Because here in red, you can see the simulated Wasserstein distance, okay, with the confidence bands, which are very tight. And in blue, you see our theoretical upper bound. And so the two appear to be very tight. Okay, so this was an example. Then you'll hear more about, you'll hear another example on additive structures further on. But now I would just like to end with a slide on some open problems that we are facing right now. So first of all, I would like to focus your attention on the fact that we measure dependence as distance from exchangeability. But exchangeability is only one extreme situation, the other one being independence. So we would actually like for a measure of dependence to also give us some information on how close we are from independence. And well, we are thinking of doing that in this way. So first, we conjecture that the maximum distance from exchangeability is actually attained under independence. And then we can use this information to build an index of dependence between 0 and 1 through normalization. And once again, this would give us an index of dependence, which is tractable and principled between vectors of random probabilities that are attained as component-wise transformations of vectors of CRVs, regardless of the particular choice of transformation T that we apply. Okay, so all this, my topics are actually have actually focused on quantifying the prior dependent structure so far, and then we would actually like to measure the dependence also a posteriori, so after seeing the data. And our idea here is that by actually comparing through the Wasserstein distance the CRV a posteriori with the CRV that one attains under exchangeability, we can actually perform homogeneity tests in a multiple sample context. And in this way, we will somehow extend to a non-parametric framework the ideas of Baccaiato, Holmes, and Diaconis 2015. Then, well, I'll just say a couple of words on another direction that we would actually like to take, which is the one of focusing on dependent random measures that do not have jointly dependent increments, okay? So vectors of dependent random measures that are not CRVs. And this is actually has many notable cases in the BMP literature, and for example, the hierarchical and nested processes, which will be described in detail by Igor further on. Okay, so I guess this is all. If you have questions, they're more than welcome. If not, I leave the floor back to Igor.
Yeah, but I think we are done. We should let Lima speak.